Here's page 17 and 18. First, let's review what the meaning of a derivative is when we're looking at slopes of lines and curves. So if you look at this picture right here, we have a curve in red, and we've drawn tangent lines, these blue lines that are in the same direction of the red curve at various points. And each one of these blue tangent lines, of course, has a slope. And if you look and think about what we talked about during the investigation, all the positive slopes look like they're going up, as far as like if you have like some kind of graph showing the economy of Brazil, you would like to see the economy going up. So you see things going from the bottom left corner to the top right corner. That is a positive slope, right? A negative slope looks like the economy of Brazil is going down. You start from the top left corner and go to the bottom right corner, and different variations of that. I've drawn them here in red. Okay, so those are negative slopes. Now, what if you have a slope that is exactly horizontal? Okay, so that doesn't look like a green slope, and it doesn't look like a red slope because it's not going up and it's not going down, which means that it's exactly flat, which means that it's not positive nor negative. It is zero. Okay, so this yellow slope here is a slope of zero. So, one thing you notice when you look at this slope of zero, or if you look at this slope of zero, these slopes of zero occur at the exact peak of a hill or at the exact bottom of a valley. So we could also call those points maximum and minimums. Okay? So it turns out that if you do find a gradient or derivative function, and you find out when this gradient or derivative function is exactly zero, that happens to be the point where the curve is at a maximum or a minimum. Okay, so let's go do the first problem. So here we're going to look at many different curves, and we're going to find out when these curves have a derivative of zero, and we're going to do it similar to the way we did it before, where we're going to take the function and call it the blue function, and we're going to find the derivative function and call it the red function, and the derivative function of x squared minus 6x, y dash equals 2x minus 6, right? And so now we're going to put both the blue function and the red function in the calculator. The blue function we put into y1, we're going to put x squared minus 6x. And in the red function, we're going to put 2x minus 6. And we're going to look at the table. Looking at a graph might be a little bit confusing, that's why we look at the table. And we want to know when the dy dx is 0. Remember, dy dx is another way of saying y dash, which is another way of saying f dash. When is the red function 0? So let's see. Oh, there, it's 0 right there. So the red function is 0 at x equals 3 and y equals negative 9. So they only ask us for the value of x, so we could just put x equals 3. Okay, let's go to number 5. So number 5, we're working with the blue function, x cubed minus 27x. So we're going to put that in the calculator along with the red function. So let's find the red function first. Let's find the derivative function. The way we find the derivative function is we take the derivative of x cubed, which is 3x squared. We take the derivative of 27x, which is 27. Let's just fix that too. I wrote it really messy. And let's put the blue function in y1. The blue function is x cubed minus 27x. X cubed minus 27x. And the red function is 3x squared minus 27. 3x squared minus 27. And we're going to look at the table. And the red function is 0 at x equals 3. Whoa, same thing. What a coincidence. Just a coincidence, guys. It's not. The answer to all these problems is not going to be x equals 3. Okay? Let's just check to make sure I did indeed put the new functions here. 3x squared minus 27, yeah. And you know, if you ever want to check these by hand, you could just take the 3, you put it here, 2 times 3 is 6, 6 minus 6 is 0, so it works, right? You could also check this one here. You could put 3 into x squared, that'll be 9, 3 times 9 is 27, 27 minus 27 is 0 also. So, okay. Let's go down and do number 9 now. Oh, that's quite a function there. Let's find the red function, the derivative function of this function. So we're going to take 2, and we're going to multiply it times 3x squared, which would be the derivative of x cubed, minus 9 times 2x, which is the derivative of x squared. 12 is the derivative of 12x, minus 7, the derivative is 0. Now I'm going to simplify this, so it'll be 6x squared minus 18x plus 12. Now I'm going to put the blue function and the red function in the calculator. So we'll put the blue function here at the top, 2x cubed minus 9x squared plus 12x minus 7. And the red function, I'm going to put the derivative of that, which is 6x squared minus 18x plus 12. And I'm going to look at the table. And wow, there's actually 2 points. There's 2 points that have a derivative of 0. X equals 1 and x equals 2. Okay, so we could say that that would be the two solutions for this case would be x equals 1 and x equals 2. Okay, let's go on to number 13. So this function, if we take the derivative of it, is going to be, forgot to put y dash there, 2 3x squared minus 6 times 2x. Derivative of 7 is just 0, so we don't write that down. We simplify this, we're going to write 6x squared minus 12x. Okay, now we're going to put the blue function and the red function in the calculator. So the blue function is, let's see, 2x cubed minus 6x squared plus 7. And the red function is 6x squared minus 12x. 6x squared minus 12x. Okay, and I'm going to graph this. And I got here 2 solutions. I have a solution at x equals 0, and I have a solution at x equals 2. So I'll write those 2 down. Okay, now the one for 17. So 17. I'm going to rewrite the blue function first. The reason why I'm going to rewrite it is because it's kind of hard to take derivatives of fractions like that. So I'm going to rewrite it as 9x to the negative 1. Remember that if you have a denominator that's a variable, you can rewrite it like this, so that you just put the power of the denominator and then you just make it negative, and that means the same thing. Now let's take the derivative of that, make the red function. So the derivative of that function is 4, because the derivative of 4x is 4. and plus 9 times negative 1 times x to the negative 2, because I take the negative 1, I put it out front. I take the negative 1, subtract 1, becomes negative 2, and the exponent becomes negative 2. Now I'm going to rewrite this. It's going to be 4 minus 9x to the negative 2. Now I'm going to put the red function and the blue function in the calculator. The blue function is 4x plus 9x to the negative 1. 4x plus 9x to the negative 1. You might say that, actually the blue function is not necessary to do these problems. We could just put the red function in. And actually that's true. But, I want to get you guys in the habit of having both in the computer or in the calculator at the beginning. And then if you ever need the information, it's right there. 4 minus 9x to the negative 2. Now let's look at the table. And is there any place where the red function is obviously 0? Well, this is going to be a challenging one. I don't see any zeros here. So the challenge here is that the zeros actually occur in between, right? And I can see two places where they might occur. One place is right here, because you see I have a positive 1.75 and then I have a negative 5. I know there's a 0 in between these two. So to see where it is, I'm going to change the step size to plus 0.1. And then, oh, there it is. So one of the zeros is at negative 1.5. Okay, and if I couldn't find it there, I could do plus 0.01, and then I would probably definitely find it. Okay, so one of the possible zeros is negative 1.5. The other one, did you know? Well, let's go back again to or plus 1, and then I'll show you where the other one is. So do you see how also there's a negative to positive transition here? So there's a 0 in between these two too. Let's go down here, and now we're going to change the step size again to plus 0.1. And then we can see that, yes, at positive 1.5, there is also a 0. Okay? All right, that was 17. Now we're going to go to page 18. Continue on with page 18 here with number 1. Determine the coordinates of any turning points on the given curves. Remember, a turning point is like a maximum or a minimum. For each, determine if it is a max or a minimum. Check your answer by using the GDC. Okay, now I am not going to have you do these completely without the calculator, because there isn't much point in doing that. Okay, now, like on the previous page, we do need to find the derivative function in order to put the blue function, the red function in the calculator. The blue function is this one. What will be the derivative function, the red function? We will take the derivative of the blue function, and that'll give us 3x squared minus 9 times 2x plus 24. And the derivative of negative 20 is 0. Okay? So here I can simplify by writing 3x squared minus 18x plus 24. And we want to know when this red function has a derivative of 0, because that tells us where the maximum and minimum are. Okay, and let's take a look. And then I'll show you how to confirm it in a very easy way. So we'll have, so in the blue function, we're going to put x cubed plus 24x minus 20. Okay, x cubed, x cubed minus second insert minus 9x squared plus 24x minus 20. Okay, and the red function is going to be 3x squared minus 18x plus 24. And we're going to do look at the table now. And we're going to see, oops, remember how I changed the step size to 1? I want to, or 0.1. Let me change the step size back. So I'll put second table set, and I'll put 0 and 1 here. And now we're going to go back to the table. And okay, so there's two places that the red function is 0, x equals 2 and x equals 4. Okay, and let's get the coordinates of the function. Do you see that one of the coordinates is 2, 0, and the other coordinate is 4, negative 4? When we get coordinates, we want to look at the blue function because the red function is not coordinates, right? So one of the solutions is 2, 0, and the other solution is 4, negative 4. And then it wants us to figure out which one's a maximum, which one's a minimum. Well, if you kind of like do a rough graph of this, you can kind of figure it out, right? 2, 0 would be like there, right? 4, negative 4, that would be here, and then negative 4 is down here, right? So if I was to figure out like which one's a maximum, which one's a minimum, wouldn't the bottom one have to be a minimum, right? So if it's negative 4 and this is 0, this one would be a maximum and this one would be a minimum. Let's go down here and do numbers 5 and 9. This notation here is rarely used in the IB, but occasionally it is, so they want you to know what it means. And basically it's the same thing as f of x equals to whatever, okay? All right. Number 5. That's in problem 11, which I left out. So number 5, I have this blue function and I need to find the red function. Now the red function I can only find if I modify the blue function, because the blue function, if I have two things multiplied together in math studies, we don't know how to take the derivative of that. So we expand it. We're going to distribute the x to each one of the elements inside the parentheses. So it'll become 27x minus x cubed. And once we get that, now we can take the derivative of it, right? So the derivative of that function is 27 minus 3x squared. Okay? So now I'm going to take the 27 minus 3x squared and the 27x minus x cubed, and I'm going to put them in the calculator, and we're going to check to see where the maximum and minimum is using the derivative function. 27x minus x cubed. Oh, I put it in the wrong place. So in the red function, I actually want 27 minus 3x squared. 3x squared. Oops. 3x squared. Okay. And in the blue function, I want 27x minus x cubed. 27x minus x cubed. And I'm going to look at the table. And when I look at the table, I can see that there is definitely a 0 point here. And there's another 0 point there. If you're wondering how I knew there would be one more 0 point, when you have a square function, when you have a quadratic, then you know that there's usually 2 zeros, okay? So that's why I looked around for another one. So one of the points is -3, -4. So I'll write that one down. -3, -54. Not -4, -54. That's quite a bit different than -4. And the other one is going to be 3, 54. So those are two different points on the curve. And you can kind of tell that since this one's 54 and this one's -54, this one's probably the maximum and this one's probably the minimum. Okay, there's another way you could do that is you can kind of check the blue function and see that, oh look, this is the minimum because look, negative 54, and if I look at the surrounding points around it, they're higher, so that's the minimum, right? This one here, it's positive 54, and if I look around it, the surrounding y values are smaller, so it's the maximum, right? Makes sense, right? The other way you could do it is you could just graph it. And when you graph it, let's do a, what do you call it, a zoom fit. When the red function is actually kind of confusing on the graph, so I'm just going to get rid of the red function by clicking enter on top of the equal sign and then graphing again, and then I'm going to do a zoom fit so that it's not so weird looking. Zoom fit is, I think it's like numbered. Which number is it? There it is, 0. Okay, and if we look at this, we can see that negative 3 corresponds to this point, it's a minimum. Positive 3 corresponds to this point, it's a maximum. We call these local minimums, local maximums, because just because this is the local minimum doesn't mean there aren't other points that are more minimum than this one. Look over here, this point is smaller, right? It's like a lower y value, but what we're talking about is like this is the smallest point in its near vicinity. This is the largest point in its vicinity too. Okay? All right, let's go down to number 9. So number 9 is very similar to 5 in that we need to rewrite it in order to take the derivative first. Remember, the first one's not too bad. If you want, you could write it as 1/2 x, because I think that people have less trouble taking the derivative if they know that x over 2 is 1/2 x. 8 over x could be rewritten as 8x to the negative 1, right? We talked about this last page. Now that we have it written like this, let's take the derivative. We'll make the red function. It'll be 1/2, because the derivative of 1/2 x is just 1/2. The derivative of 8x to the negative 1 is 8 times negative 1, x to the negative 2. Now, if I wanted to rewrite this red function, I would put 1/2 minus 8x to the negative 2. Okay, and then I'm going to put both of these in the calculator so that we can find the minimum points. Okay, or the minimum and maximum points. So I'm going to put for the regular function in blue, I'm going to put x divided by 2. Oh, let's use the vertical number, the vertical fraction, because then we don't need to put parentheses and we don't need to worry about the parentheses. So x divided by 2, so I'll put x on top, 2 on bottom, and then plus 8 divided by x. Again, I will put 8 on top, x on bottom. Okay, and then the red function, I could have put 8x to the negative 1 too. For the red function, I'm going to have 1/2, I could just write 0.5, minus 8x to the negative 2. Okay, and now I'm going to look at the table. And when I look at the table, I can see that there's a 0 right there. So negative 4 is one of them. One of the solutions, or one of the places that is a minimum or maximum, is negative 4. And let's see if there's another one. I don't see any here. Well, there's another one, 4, 4. So there's 2. Remember how I told you that by looking at the y value, you can figure out which one's the maximum, which one's the minimum? That only applies if there's not a weird asymptote or something right in the middle of it, right? Because remember, like if you have an asymptote, you might have something weird like you got this function here and you got this function here. And do you see how this is a minimum even though it's higher than this one? Okay, so in the previous problem it worked because there is no asymptote. But whenever you get variables in the denominator, you get asymptotes, so we need to be careful with it, okay? So the safest thing to do to figure out if it's a maximum or minimum really is to graph it, okay? So let's go ahead and graph it. And I just graphed it here. Here's the blue function graphed. And I just am going to find out where the maximum and minimum are. The way I do that is I do second calc maximum. So I see that there is a maximum kind of around here somewhere. So I put my cursor slightly to the left of that maximum, slightly to the left. That's good. I'm confident that the maximum is somewhere here. So I'll click enter, and then I move the cursor slightly to the right of the maximum point. I'd say that's good. Hit enter. Guess doesn't matter. Maximum is -4 comma -4, which we did know that was a maximum, right? So let's mark that maximum. Let's figure out 4 comma 4. 4 comma 4 looks like it's around here, and it looks like it's like a minimum point here, right? Because like everything else is higher than it, okay? So if we want to actually find this point, if we want to make sure that it's a minimum, then we go to second calc minimum, and we move the left bound point slightly to the left of here, because that looks like it's the minimum. Okay, and then we hit enter, and then we move the cursor slightly to the right. Okay, and then we hit enter, and the minimum point is 4, 4, just that point right there. So that is the most reliable way to figure out if it's a max or minimum. You can look at the graph, you can tell it's a max or minimum. If you want to, you can use second calc maximum, second calc minimum to verify that it is indeed these points, okay? And you might say, well, why even do the derivative? You didn't need to do the derivative to find out the maximum and the minimum were -4, -4, and 4 comma 4, and that is absolutely true. Usually on the IB exam, in the part where they find maximum minimums, they will force you to find the derivative by asking you to find the derivative first, okay? That's how they force you to do the derivative. But indeed, to find out if something is a maximum or minimum, or to find a maximum minimum, if they don't ask you to take the derivative first, in math studies, you don't need to because you got the calculator, right? Thank you.